3, which has lots of good tangent and cotangent graphs for us to look at. So for A, when it says sketch several cycles of the graph, it's a good idea to kind of go through the stuff in your head that we've been doing where you're thinking, okay, A is 2, I have to remember, thank you, to stretch this out, you know, when I get to the graphing part here. Looking for a B value, and there isn't one in front of the X, so that means that the period is going to remain pi. And we didn't get a formal box for that formula when we did tangent and cotangent, but remember that the period for this, any of these tangent or cotangents, is just going to be 1 pi over that absolute value of B value, whatever we find there, if there is one. And then I look at the 1 in the back and I say, well, this is going to be a vertical translation. Up 1. So I start thinking, do I need helper lines and all that good stuff with this one? Well, I'm going to need a helper line probably for the up 1, you know, to remind me. And I'm just going to put a little 1 right here and a negative 1 right there. Okay, I'm not supposed to start from the x-axis. I'm supposed to start 1 up from there. But we don't have a phase shift to show us that there's a new position to start in. So basically, we just have to remember our x-axis is kind of up 1 here. But the good news is we didn't have any b value besides the 1 that's already there, which means we're still talking negative pi over 2 to pi over 2 for our vertical asymptotes. Oops, I'm off up here. And halfway between those two is where we're going to find our 0. But again, remember, this is not the axis anymore because we're moving 1 up. It's going to be right here. And then this tangent, is that the one that's always increasing or always decreasing? Which one? It is increasing. So the only last thing I have to think of here is I'm supposed to go up 1 and over 2 with this one. So over 1 increment and up 2. Back 1 and down 2. And then it says just several cycles. Okay, so we're going to go from pi over 2 to 3 pi over 2 because that would be another 1 pi. And maybe I'll go back to negative 3 pi over 2. But we're going to do the exact same thing. We're using that same 0 that's been moved 1 unit up, and we're going to go over 1 and up 2, back 1 and down 2. For both of those positions. Not bad, huh? Yeah, tangent and cotangent. A little easier to work with than sine and cosine. All right, so let's look at B. B's looking pretty basic, but see this negative in front here. You know, that negative for cotangent. So we have to remember that this is going to be a reflection over the x-axis. What else would be new and different from the parent function with this one? 1 down. Vertical translation. 1 down. Is the period going to be messed with in this one? No b value again, right? That's pretty cool. So we can keep our asymptotes where they're supposed to be. But we need that little helper. We've got a vertical translation 1 down, so put some labels on there. Get that helper on there. So remind me again, where are the asymptotes for cotangent? Good. 0 and 5. And while we're at it, because we know they want several cycles, we might as well put a couple more of these on here. So a period of 1 pi, we're going from 0 to pi, it's also going to be from pi to 2 pi, etc., all the way around. All right, now, cotangent with a negative in front of it. So if you take cotangent and you reflect it over the x-axis, what's really happening? It's becoming tangent. Exactly. So instead of thinking negative cotangent, we could just think tangent here. And then use the thinking that we had over here. You know, halfway between is where we're going to have, and remember we've been moved down by a vertical translation 1 there, so that's going to be our 0. Or, and I absolutely understand if you want to do this, where you're thinking, okay, cotangent, normally I'd have to decrease, so it's going to go like this. I'm here, but uh-oh, I have to reflect it. So now it's going to go down here. If you want to think through those steps, instead of thinking, oh, cotangent with a negative in front is tangent, no problem. You know, feel free to do that. But we did not have a vertical stretch or compression with this one, so over 1 and up 1 and back 1 and down 1. And we'll just do that a couple of times. I was just thinking here that I should tell you, because people would make this mistake last year. You want to fill that up to the vertical asymptotes. Make it look like they're asymptotes. Remember, asymptotes, you're supposed to approach them. So you need to look like your graph is approaching those asymptotes. Don't just kind of make a squiggly right in the center and say, hey, good enough. You know, we need to have something that shows that we understand what asymptotes are going to do. All right, well, those two aren't so bad. Oh, this one has a g value. So let's see what happens here, and it has a little phase shift for us. All right, well, we can do this. So this 2 is going to affect our period. So this will be pi over 2. So it's not 1 full pi anymore. Makes sense. That 2 in that position tells us it should be a horizontal shrink of half as much. Yeah, that's going to do it. But this one also has a phase shift. Where are we going with this? To the right. So we're going to the right. But no vertical translation this time, and our a value is still 1. But helper line this time, and notice we didn't put the intervals on this one. We're going to have something at pi over 4. So we can kind of think up here where these were already marked. This wouldn't be bad. I mean, it'll kind of squish them a little bit if we go to pi over 4, but 0, skipping the pi over 4, going to pi over 2, that wouldn't be a bad idea. Not that far off from that. So we've got, I'm not marking everything again because it'd be too hard for everybody to see for me. On my paper, when I do these homework assignments, I mark every single one. So I do pi over 4, 2 pi over 4 is pi over 2, 3 pi over 4, 1 pi, and every 4 more we'd have another pi. What I want to see on the test, Ashley, is that you have everything for at least one primary period. So if you give me everything for this one from pi over 4 to, let's see, we're going to be going up 2. So if you give me everything from pi over 4 and then you go 1 period to pi over 2, everything from pi over 4 to 3 pi over 4, I will be happy. Because that shows me you took the time, you went through one primary period of the graph. And the rest of them make sense from what you've done. I don't expect everybody to sit and give me every tick mark on everything, but I need to see enough of that primary one to know that you know what you're doing. Okay? All right, so there's my x's. Might as well go by ones again on the y-axis. But we definitely need our little helper with this one, and our helper is going to be this pi over 4. And by going through that with Ashley, I just kind of talked us through, where we're going to need that other asymptote at. We had pi over 4 for our new starting position on the horizontal axis, and we had 2 pi over 2. Wait a minute. 1 pi over 2 up here. Yeah, we're talking tangent. And we needed to find out where would that end at. So that's at 3 pi over 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4. Now here's why I didn't want to change the intervals. That looks a lot skinnier than the one that we did above it. Is it supposed to? It's supposed to be half as big, isn't it? So that's why with the intervals, sometimes I'll force you guys to pull this in a little bit closer so you can see that. So now, we talking tangent or cotangent? So increasing or decreasing? Increasing. So right smack dab in the middle, we have that. And we have a new A value. So basically it's over an increment and up one, but in this case, notice how this is so squished, we're going to go over a half and up one, and back a half and down one to get that. And that, you're going to see, is a little different from sine and cosine, because when we did sine and cosine, I had everybody figure out, okay, these are all the positions. Now let's go ahead and find them. With this, I want you to see, this should be skinnier. It should be than what we saw up there. And then what we do is notice, hey, I'm going to go every 2, and I'm going to put another vertical asymptote on there. And it said several of these, so I probably better make several. Several of these for me would be 4. I mean, that would be enough. Again, just comparing that to A that's right above it, and notice, oh yeah, it looks like it's been a horizontal shrink. Everything's kind of squished together there. All right, let's go to D. Looking at D, got a new A value, right? Are we going to have a new period for this one? We are. We got a 3 sticking in front of that X. We're going to have to do a little factoring here and see how that all works out. So let me move my A equals 2 down a little bit. So y equals 2 cotangent 3 times something. Okay, well obviously this first one's X. And if we're thinking, okay, how did we pull a 3 out of there? Well, then just say, what would happen if I divided pi over 2 by 3? Well, we'd have to multiply by the reciprocal. That's going to make that pi over 6. Things just got a little interesting here, because that's going to change our period. Normally, pi over b. And in this one, that's going to be pi over 3. So we've got a phase shift. And what's our phase shift? Which way? To the right. So this time, I'm not going to stick with our normal pi over 4 as our increments for each one, because we need to see this in a little bit more detail. So we've got our little pi over 6. And we want to know, hey, where is this going to end? Well, there's two ways we could do it. We can set this up as an inequality again. We could say, okay, normally it would be from 0. Better check. This was cotangent, wasn't it? Yep, 0 to pi. But now we have some stuff affecting x. That's our 3x minus pi over 2. And remember, this will give us our ending and our starting place. So we could add pi over 2 all over the place. And then divide everything by 3, which is the same thing as multiplying by 1/3. See that we're going to be going from pi over 6 to pi over 2. So let's see. If we go by 6, I'm going to spread this out a little bit. I'll use 2 increments so it can be seen from the back there. There's pi over 6, and another pi over 6 would be 2 pi over 6, which would be pi over 3. And so now we've got 1 pi over 6, 2 pi over 6, 3 pi over 6, pi over 2. Hopefully we can make that out.
How can we see to find out where to go to just add
I'm giving you, Maggie's got a good question. I'm giving you 2 different ways. How many of you really like the interval with the inequality piece in? I do too. I mean, I don't know what it is about it, but it just helps me start figuring out where's the beginning and where's the end. Some people, they just look up here and they say, well, all I'd have to do is add the period. Why don't I just do that instead? So there's more than one way to get done what we need to get done. You definitely could use that inequality stuff with this one as well. You know, it's just up to you which way you want to go. Alrighty, so I have it on there, and now I know where this is going to begin. So we have our phase shift that's leading us to this new pi over 6 piece. Right there. And we know the period with this one is going to be pi over 3. So we're finding that new spot where it's going to land. Well, that was right here. That's our pi over 2. So now let's go back and see all the things that we have to keep track of. And if there are any more Hooper lines we need to go through. Do we have a vertical shift? Don't need a helper line for that. But we are going to have to keep track of the A when we get to that point. We do know halfway between. There's where we're going to hit that axis, right there. A cotangent, is that always increasing or always decreasing? Decreasing. So what we have to do is go back 1 and up 2 to get that amplitude of 2. And then we're going to go to the right 1 and down 2 to make sure that amplitude stays correct. And again, make sure it looks as though your graph is going to approach those asymptotes. So now, like I was talking through with Ashley, you wouldn't need all the tick marks again. You could maybe say to yourself, okay, I've got pi, this was 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, 5, 6, and just put pi on there. 2, 3, 4. Do it that way. Because this one has that period of pi over 3. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and 1 off. Because we don't necessarily need all the labels after this. But it would be good to have your asymptotes labeled. And then you just recreate it.
Did the phase shift just happen to be like in the middle of both of the asymptotes?
The phase shift,
Or the periods?
and that we won't know until we know what B is. So with some of them, it's going to happen. Yeah, we're not guaranteed that that's how it's going to happen. So we just really have to go through the math, do the inequality, or add the period to see where it's going. Cotangent and tangent, not so bad. 43210, we just on graphing cotangent and tangent before we go on anything else. Okay, not horrible. Better numbers than for a lot of people than what I saw for cosine and sine. Now, it's a good thing we are going back to cosine and sine again. But you turn the next page and you're like, liars here home. Cosine and sine, this is supposed to be secant and cosecant. To graph secant and cosecant, we're going to do exactly what we did for cosine and sine. But we're going to turn them upside down because they're reciprocals for those graphs. So when we talk about these, we're going to work on our skills for graphing cosine and sine as we're going through to graph secant and cosecant. So our secant function, remember, is what we get by flipping cosine. So maybe write yourself a quick little note. That's 1 over cosine. Because what that does is it helps us think through, oh, there's going to be some vertical asymptotes again. Because wherever cosine is 0, this is going to be undefined. And here's my cosine in the blue. Those are where my asymptotes are going to be. At pi over 2 and 3 pi over 2. We'll have some asymptotes. But we're still going to have asymptotes, and that is a characteristic. So characteristics of the secant function, those are inferred from the fact that it's the reciprocal function of cosine. So obviously these are really, really related to each other. They really are. So I go back and think about cosine and how we graphed cosine. And I remember that the period for cosine was 2 pi. So we would mark, typically we would mark 0, pi over 2, pi, 3 pi over 2, and 2 pi for that. We're going to mark the same things when we're working with cosine, unless of course there's some kind of phase shift that's going to mess with that. So the reciprocal of this piece, secant, is 1 over cosine. So it still has a lot of things that were going on with tangent, but more closely resembles what we did with cosine and sine. So I'm going to go ahead and put some numbers on here that would make sense from what I know about cosine. And that would be using negative pi over 2, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then it was 1 and negative 1 for our parent function for this. So cosine. Cosine was Kahala. Because with cosine, we were supposed to start high, axis, low, axis, and then back to high. Now just do the dots. Don't do any graphing of the actual function yet. So now I'm going to go backwards and put my dots on there. By graphing what we know about cosine, we have just graphed where those asymptotes have to occur. Wherever cosine is hitting the x-axis is a 0 for cosine. That's where our asymptotes are going to have to go. So we're going to have an asymptote right here through negative pi over 2. We're going to have an asymptote right here at pi over 2. Another one at 3 pi over 2. I start thinking, hey, those are the odd integers again when we put them in front of here. This would be negative 1, 0, 1, 3, 5. Those will be where those vertical asymptotes are taking place. Now here's the cool part. We learn absolutely nothing new when we graph secant. What we graph for cosine is exactly the same. We just turn it inside out. we use this point to tell us that the graph is going to go downward, because that point is on the lower side of the x-axis, below the x-axis. This one is above it. Turning this graph inside out would do that. Now notice that I carefully make sure that my graph is filling the space so that it looks like it's approaching the asymptotes. Don't ever graph these with just a little quick parabola in the middle. Make sure you're filling up that space with your graph. And they should be nice smooth curves, but they also should look like they're definitely approaching the asymptotes. We don't want to just slap anything in there. That was not new. That was Kahala. That's all we did. We just turned it inside out. That's it. So you find those zeros from graphing cosine, make those your vertical asymptotes because they're going to be in the denominator and we can't divide by 0. And then you turn it inside out. That's what we do. So with secant, because cosine had a period of 2 pi, secant has a period of 2 pi. Zeros, none. It's never going to cross the x-axis. And we're turning it inside out. Vertical asymptotes, that's where the cosine of x equals 0. And like I said, it gets kind of weird because we'd like to just say in words, just use the odd integers, but you can't do that. You have to describe it mathematically. So all x's where x equals pi over 2 plus n pi, where n is the set of integers, And if you're hoping for something on your paper that you can see, it's the domain. We just take off the not equal to when you do the vertical asymptote. So it's probably easier for you to see it on your own paper. It is there. We did give you that one, didn't we? Oh, rats. She covered that one up in the box. All right. So x such that x equals pi over 2 plus n pi, where n is an element of integers, an element of z. No horizontal asymptotes. Not going to happen. And the domain is everything but those vertical asymptotes. So that's just putting a not equal to in that. So the set of all x such that x is not equal to pi over 2 plus n pi, where n is the set of all integers. Our range here, we've got a gap. We don't use all the y's. There's a gap between -1 and 1 where our graphs are not occurring. And so that gap is going to be filled using interval notation where we say, hey, from -1, negative infinity to -1, including -1, then we have to make a little jump. And that's what that union is for. We're not going to be using this, but we are going to go back on the other side and do 1 to infinity. So a little jump due to the range there because of the gap. Continuity, it is continuous over its domain. It's really, we can't just say continuous. We have to say continuous on its domain. Because we're leaving off those vertical asymptotes. We have to be specific. Symmetry. Back up and take. Well, if I were a really good drawer, it would have symmetry over the y-axis here. That would work. We would be able to see it. So that means even. Now that's a good thing. Because notice, it's telling us if we have a negative in front of the x for this, we can basically just ignore it. Because it's even, it's going to give us the same graph on both sides. So sometimes if there's a lot of negatives in a problem, that's an easy way to get rid of it, is to remember, okay, cosine is even, so is secant. You just kind of visually think your way through that. And you won't need that extra negative. This does have extrema. It does. There's a minimum of 1 at x equals 2n pi, where n is the set of all integers. Okay, well, we better go back and take a look at that. Minimum of 1 at 0 and at 2 pi, and we can infer it's going to be 3 pi, 4 pi, etc. And that's why this is saying what it does. So minimum of 1 at x equals 2n pi. 0, 2, 4, etc. And then we also have a maximum of -1 at pi plus 2n pi, where n is the set of all integers. not bounded above or below, because our arrows are showing that we're going forever upwards and forever downwards. We just have that gap in the range right in the middle where we don't have anything graphed. No new instructions on graphing other than you get the points on there and then turn it inside out. That's the new instructions. So next up, cosecant. Cosecant is just what we get when we flip sine. So this is going to work the same way. We're going to graph what we know about sine, and then we're just going to turn it inside out. That's all we do. So as I look at this, I'm thinking, well, okay, if this is 1 over the sine of x, now my zeros are in those positions, because that's where sine is 0, is those positions. Not new. We look at this and think, okay, well, it's still sine. Its period is 2 pi. We'd still use pi over 2, pi, 3 pi over 2, and 2 pi. Well, that's what we're going to do. Still using that 1 and negative 1. And then all we had to do for this one was say, okay, it's Sahala. Sine is axis, high, axis, high, axis, low, axis. Again, just put the points on there. Don't do our. Sometimes you get this far and it's automatic to just draw it in. I've got sine here. But this isn't sine, this is cosecant. So what we just found by putting what we know about sine in there is where our vertical asymptotes are going to be at. So we go back and say, well, if sine is 0, this is going to be an asymptote. This is going to be an asymptote. So will that, and so will that. And the position of our lovely dots, high or low, tells us where our branches need to be. So this one is below the branch, going down. This one is above, and again, I'm trying to make sure that I'm filling up the space that I have between those asymptotes to show that I understand what an asymptote is when I approach it. I never quite get there. Same graphing that we did with sine, just turning it inside out. So the period is still 2 pi, zeros, none. You know, our little branches never cross. The vertical asymptotes, now it's where sine is equal to 0. So that's all x, such that x equals n pi, where n is the set of all integers. -3, -2, -1, 0, 1, 2, 3, etc. All horizontal asymptotes, again, just like cosecant. And then your domain is the same thing as the vertical asymptotes, just with a not equal to. Because for the domain, you can't use those vertical asymptotes. So x, set of all x, such that x is not equal to n pi, where n is the set of all integers. Range is the same as it was for cosecant. We've got a gap. We're graphing from negative infinity up to -1, but then we have a gap up to 1 and 1. It is continuous over its domain. Again, very important that we say continuous on its domain. Those vertical asymptotes cause a problem. Check for symmetry. Yeah, it is odd. It's the same symmetry that you have with sine. You know, it's odd. That's what the symmetry is. So what that tells us is we can move the negative, but the negative is not going to disappear. When we're talking about even, that's a nice feature of even, where you can get the negative to kind of disappear because it is even, but not with the odds. So we can take that negative that's in front of the x that kind of messes with us because you know, we're looking at B and we're trying to figure out what is the period and all that good stuff. And we could just put it out in front and think of it as a reflection. And then the local extrema, we're still looking at a 1 and a negative 1, but different locations this time, sliding it over a little bit. So just like we talked about the phase shift, making cosine be sine, sine be cosine, it's the same thing here. So minimum of 1 at x equals pi over 2 plus 2n pi, where n is the set of all integers, and a maximum of negative 1 at negative pi over 2 plus 2n, where n is the set of all integers. Got bounded above or below. Arrows are showing we're going up forever and we're going down forever. Well, we ought to be able to get at least one of these out of the way, if not both, huh? So, switch gears, and a tangent is nice. Example 4 has us sketch at least 2 cycles of the graphs of the following equations. And looking at A, the first thing I notice is they're using decimals, and that just is messing with our heads. So let's go ahead and change the 0.5 to 1/2 cosecant negative 2x minus 1. And then we need to consider whether or not we can move this negative or if we can just drop it all together. So cosecant is what we get when we take the reciprocal of sine. And remember how sine works is that we start at 0, 0, and then we go pi and axis. So we see by the little graph here that this is odd. And for odd functions, we cannot eliminate that negative. But what we can do is we can move it. And it would be nice to have that out front so that we can take care of that as kind of a last step. When we get to thinking about graphing this and we're talking about that amplitude, we can just remember that we also need to do the reflection there. Now, cosecant, as it is the reciprocal of sine, will have a normal period of 2 pi, so 0 to 2 pi. But we have a b value of 2 in here, so we're going to put our 2x in, and we'll have dividing by 2. 0 is less than or equal to x, which is less than or equal to pi. So better for this one to say, okay, if 2 pi divided by b gives me pi, I'm going to go back to graphing like I did cosine and sine before and think, well, I need 1/4 of that. So I'm going to graph with pi over 4 and just go in increments of pi over 4. And I have 1 pi over 4, 2 pi over 4 would reduce to pi over 2, 3 pi over 4, and then 4 pi over 4 is 1 pi. And we could continue on if we wanted to here. We've got 4 pi over 4, 5 pi over 4, and then 6 pi over 4, which would reduce to 3 pi over 2. And then a little backwards as well, because like it said, sketch at least 2 of these cycles. So we'll want a negative pi over 4, negative pi over 2, negative 3 pi over 4, a negative pi, negative 3 pi over 2. All right, so I do see that there is a vertical translation, 1 down. And so what I do is I think about the fact that I have that a is a negative 1/2, and I have that vertical translation 1 down. And I think I'm going to go ahead and go every 2 blocks here for 1 to try to keep that a little bit more stretched out so it can be seen. Now the next thing we would do is we would put in our helper, and our helper for this one is that moving down 1, and that's going to be dashed or dotted so that we know that this is just a helper. But it's also, you know, where we have that new axis, and so that's what we want to keep track of. Now, we have taken care of everything we need to. We have the period on there. We have that vertical shift 1 down. And now with cosecant, we think about how do you graph sine. And there's no phase shift, so we're going to start normally what would be 0, 0. We're now going to start at 0, negative 1, because this one has that vertical shift, vertical translation of 1 down. And then normally sine would be Sahala, axis high, axis low. But remember, we moved that negative out in front to make this easier. So instead of sine axis high, we're going to go axis low. And I want to go just one block, because remember I had one block going for a half. So it'll be axis, sine is axis, low axis, then high, then axis, then low, etc. And what I'm looking for as I'm doing this pattern is I'm trying to figure out where I have a value of basically 0 on my new axis, because my new axis is what's going to be important to me since this has all been translated down. And any of those spots where I have a 0 on my new axis, those are going to be asymptotes. So anytime one of my points for sine has landed on y equals -1 is where I'm going to have an asymptote. So I have my asymptotes drawn, and now I remember that cosecant is like turning sine inside out. So what I need to do is make some nice branches here that fill up the spaces in between the asymptotes, because that shows that I understand what an asymptote does. That an asymptote is something that I approach, but I never cross. We don't want to just slap something in here and hope it's good enough, especially on a test. We want to make sure that it's evidence we know that this is going to approach that asymptote. And we have it. So we look at this and we make sure everything's going the way it should. We had a negative in the front. That meant we should have had a reflection. And we should have an a value of 1/2. So notice from our line y equals -1, we're going up 1/2 and down 1/2 in order to get started with our graphs. Our period was to be 1 pi, and in order for a period of cosecant to work, we would have to see both a down opening and an up opening, and we do. We have a down opening and an up opening portion of that graph. So we have everything that we need for y equals 1/2 cosecant -2x, the quantity -2x minus 1. And now I decided not to do the next one in class because this one is just ugly. We have a weird b value, and it'll be a good thing to review when you come back next week. And then hang on, because on Monday I'm kind of saving that goofy one on purpose.